Hello and welcome to this walkthrough of the A2 EEE mock from March 2016, and you'll need to use this to help with your exam technique mainly if you tried the paper a second time with your notes like you were asked to do over Easter. Please make sure that you've done that process before you start looking at this video clip. The clip will be approximately 45 minutes to 1 hour long, so make sure that you're able to fast forward it to the questions you need. Make sure that you really have tried to think your way through the questions yourself before going through the relevant part of this walkthrough. And basically, any examples of things you need to read on the question will be highlighted like this. So, obviously, a couple of the questions were left out, weren't they? Because we hadn't quite got to that stage, and we were trying to keep the paper down to 1 hour and 30 minutes. So in this particular walkthrough, I've uploaded the whole PDF, so you can assume that question 2 and question 4 are omitted like they were from your paper. So therefore I won't be bothering with question 2 and 4. So let's start with the first question. It says, this question looks at transition elements, ions and complexes, and it asks you, what's the oxidation number of chromium in the complex ion CrOCl5 2-? So the way you can do this is to make sure that all of your oxidation numbers add up to 2-. Make sure that Cl5 is -1. Make sure that oxygen is -2. So that must mean that the chromium is left being +5. And the next one, what it asks you to do is a reaction catalyzed by a named transition element, compound, or ion. So the reason I put any appropriate equation or matching catalyst, that means you can choose from a number of them. And in any part of this paper, what I'm not going to do is go through all the ECFs in the interest of keeping this clip fairly short. So a little sort of note to you. So that applies throughout this paper, or this walkthrough. The next part is an octahedral complex, and it's C9H30N6Ni3+. So it's bonded to, or the nickel rather, is bonded to 3 molecules of a bidentate ligand. So what I suggest is what that actually means is that part can be divided by 3. So that will help you down here. So the first thing to do is to do the definition of a bidentate ligand. So what's underlined is critical. It's really important that you say it in that way. You can say it in slightly different ways, but provided you say it's 2 electron pairs, in other words, there's 2 pairs of electrons, and there's 2 coordinate bonds that are made. Okay, so let's move the page down slightly. So the molecular formula of the bidentate ligand B, we said a little bit earlier, didn't we, that you're multiplying dividing C9H30N6 by 3. So it's obviously going to be C3H10N2. So where it says draw a possible structure means that provided it's a correct structure, you're able to draw either the skeletal, the displayed, or the structural formula. So I'm going to put the 3 possibilities in. So anything along those lines, provided it's legitimate and correct, will get you that mark. So then you need to say how B is able to act as a bidentate ligand. So it's led you towards this, hasn't it, through the course of the question. So if you asked me how to do the perfect answer, that's what I'd put, because that covers you for all eventualities. You say exactly where the lone pair is, you say which group that atom is on, and you can say what the lone pair of electrons is going to be doing. Alternatively, You could as well, if you wished, put the lone pairs on the nitrogens like I'm doing in blue. Like that. You might just make them a little bit bigger. So for example, if I want to do it properly, perhaps I might do it like that. So it's actually visible to the examiner. I may be being a little flippant there. So make them nice and visible. So that's one possibility. But you'd still need to mention them. Say something about them in words. Okay, the next one is about coordination number. Now remember what the coordination number is. It's slightly different to the oxidation number, isn't it? So bearing in mind it's the number of data equivalent bonds that the central metal ion can take part in with a ligand or ligands, you need to count up the total number that are happening in complex ion A. So it's octahedral, if you remember. They told you it was octahedral, so that means it's going to be 6. Okay, so let's go on to the next part of the question, which is about drawing the structures. So a really important tip here is to read the question. I noticed when I marked this, a lot of people have forgotten to do that. Now it's not wrong to do the full-on structure of the ligand, it's only 1 mark, so save yourself the work and use the time later when you're going to be focusing on harder questions. So here you can simply do this, a line to represent the bidentate ligand. The thing I would say though is to make sure that it's definitely mirror images. Make sure they're well connected up, like that. So why am I making a point about this? It's because it's optical isomers. So although it might seem like an easy thing to do, it's also an easy thing to get wrong because of its simplicity. So when it says, next, describe the reactions of either aqueous copper 2 ions or aqueous cobalt 2 ions, what I'm going to do is both, so you can see which ways it could have been done. I'm going to start with copper. So whichever one remains highlighted is the one I'm doing. So with that in mind, what I'm going to do is change the highlighting. And I'm going to highlight it in red. A, because I can, and B, because it matches what I'm writing. So what would the world be without colour coding, eh? So let's start with so in these answers what I've done is I've linked the observations with the equations clearly by putting underneath each one what's actually going on. You can obviously write it as sentences or in words, but make sure that you've got the equations right, which means going away and making sure you've learned them from your notes. So I'm going to switch over now and do the cobalt version, if that's the one that you did. So for cobalt, these are the equivalent. Make sure you've had made a note of any slight differences in appearances also, as well as the equations themselves. So for example, notice that this time you've got 6 ammonias that combine instead of 4 compared with the copper. So subtle differences, but there's also a few similarities as well. Okay, so moving on to the next question. We said we'd leave question 2. But this time we're moving on to question 3, which is about energetics. So this gives you some information that you'll need to use later on. It says, why does the reaction have a negative entropy change? So in other words, it becomes more ordered. So you've got to explain why that becomes more ordered, not just the fact that it does. So that's the kind of thing that they're after there. 5 moles of gas forming 3 moles of gas, which is an increase in order. So the next one is calculating the standard entropy for hydrogen. In other words, this value, but for hydrogen. There's an equation you need to use this juncture. So you're looking at the total of the entropy of the products, take away the total of the entropy of the reactants. So you do it using the total of the entropy of the products, take away the total of the entropy of the reactants. So inserting all of those values in here. The one of interest is this one here. So I had to rearrange the expression and it gave me plus 131. The really important one to remember at this point is that entropy is expressed as joules, not kilojoules. So this time what they want you to do is explain and include a calculation whether the reaction is feasible at 25 degrees C. So we've got to use delta G at. So don't forget the temperature has to be in kelvins. So this temperature we're looking at is not 25 degrees C, it's 298. So we have, so a couple of things to mention at this point. The 0.164 is basically the 164 from further up, converted into kilojoules per mole as opposed to joules per mole. So that's your delta S being changed into kilojoules per mole. You have to do that when you put delta S into the delta G equation. And because the delta G answer is less than 0, then the reaction is feasible. So let's move the page up a little bit. And finally, again, it says explain with a calculation the significance of temperatures above 1154 degrees C. So the first thing you should do is think, what's that in kelvins? So I'll give you the calculation again, but this time put 1427 kelvins into the calculation, keeping minus 0.164 as 0 delta S. You get 0.028 kilojoules per mole, which is technically above delta G. Technically above 0. So above this temperature the reaction becomes feasible, because if the temperature was bigger, then it would drop the delta G value below 0 and the reaction would become feasible. So let's now go to the next question. So this is one again where I noticed other people got a bit unstuck. So let's go through the question. You have 1 mole of sulfur dioxide and half a mole of oxygen. The volume is 250 centimeters cubed, so instantly you should start to think, should that be in decimeters cubed? Like that. So the mixture was reached at equilibrium at constant temperature. And without changing total gas volume. So at equilibrium, 82% of the sulfur dioxide had been converted into sulfur trioxide. So you determine the concentrations of SO2, O2 and SO3 at equilibrium, and then calculate Kc. So the first thing you've got to do is lay out your values at the start of the reaction and at the end of the reaction, the value in moles. At the start of the reaction, I just read off what it's told me in the question. So at equilibrium, if 82% of the sulfur dioxide had been converted into SO3, then therefore 82% as a decimal is that, and that leaves us with 0.18 of SO2. Now because the SO2 is 2 to 1 with oxygen, that means this one would be 0.090. So don't forget this is the moles, not the concentration. So the Kc expression would be written like that. To get the concentrations as they're in the Kc expression, you have to do this. So what I've done is I've divided all the moles by 0.25 decimeters cubed, because I'm dividing moles by volume to get concentration. So if we now do the units, let's just do the calculation first. That gives us 57.6. And to get the units, all you have to do is put in what they are and then cancel. So that's your sulfur trioxide. Same for your sulfur dioxide. In brackets. So, those can be cancelled. So that now gives us that is your unit. Could also be decimeter to the power of 3 times mole to the power of -1. But that now gets us our 6 marks. So let's move on to the next. This bit is a bit more qualitative. It says explain what would happen to the pressure as the system was allowed to reach equilibrium. So in other words, that's approaching equilibrium. So the pressure would decrease as fewer moles of gas, 3 moles going to 2 moles as forward reaction would speed up. So the value of Kc for this equilibrium decreases with increasing temperature. And it says predict the sign of the enthalpy change for forward reaction. So the first thing to do is if it decreases with increasing temperature. Let's look at Kc again. So if Kc is going down, that must mean that the bottom part is going up and the top part is going down. So the products are going down in concentration, so the reactants are being favoured. So if that happens with increasing temperature, it means the reverse reaction is endothermic, so the forward reaction must be exothermic, and therefore negative, which in itself would mean that the effect on the SO3 yield is that it decreases. So in this next scenario, the experiment is done again, but this time the same amount of SO2 in excess of O2, which essentially can be taken to mean more than is needed. So the volume is still compressed to 250. So it says state and explain in terms of Kc how the equilibrium yield of SO3 would be different. So to start off, you need to talk about the oxygen concentration because it's obviously changed. So because the oxygen is in excess, its concentration is greater at the start. So the value of oxygen increases within the denominator part of the Kc expression, which is this bit here. So oxygen itself is going up within that part of the Kc expression. However, as the temperature is constant, Kc doesn't change. So therefore, once equilibrium is reached, the yield of SO3 is greater as the excess oxygen is used up. So finally, because we've got a constant temperature, Kc is restored as the XX oxygen is used up. So let's now move on to the next question. We'd leave out 4 as well. So we're actually gone on to the Born-Haber cycle one now. Okay, so we've rolled out into the changes. What they want you to do is write the species that are present at each stage in the cycle and include the state symbols. So let's pop those in. So I'll mark each for those. So the next part asks us to define the term lattice enthalpy. So the definition should look something like that, but definitely have the 3 things that are underlined in it. So I'm assuming at this point you've got the completed Born-Haber cycle from the previous page. So I'm going to put the calculation down for you. So notice that I put in bold the 2 things that I needed to multiply by 2. Quite a common mistake is forgetting to do that. So those would be the the 2 ionizations or atomizations, of iodine, and also the 2 electron affinities of iodine. So that gives us -2473. So let's go on to the next part of the question. And here it's asking us about electrode potentials. But it starts off by asking us to do the electron configurations of iron 2+ and Br-. So in other words, for the 2+ ion, you have to take 2 electrons off what you put for the atom, and for the 1- ion, you have to add 1 electron on to what you put for the atom. So that's what you should end up with. Don't forget that these 2 are interchangeable. They could be written as 4s2 3d10. So let's now move the page up and predict the products of reacting iron separately with those 3 things. Something along those lines is what you should write for each case. So I've started by doing the one for iodine. I'll do the ones for bromine and for chlorine underneath. So those are the 2 for bromine and for chlorine. And another point down here is that Fe2+ will react further with Br2 and Cl2 to also give Fe3+. Because if we were to move the page back up and look at the voltages, the electrode potential for Fe2+ is 0.77. For bromine it's more positive at plus 1.09, and also for chlorine it's more positive at 1.36. So it's important not to forget that too. That's one of the points that very few people put in. So the next part of the question, I think actually this is the last part of the test. It's almost there, isn't it? Yeah. So let's have a look at how we read this question. In acid conditions, that H+ is a reactant, Fe2+ ions reduce NO3- to NO, and Fe2+ ions are oxidized to Fe3+ ions. So in order to work out the equations, you'll see you've actually been given quite a lot of space. So I'd suggest we use this space to do the half equations. So first NO3 being reduced to NO in acid conditions. Let's try that. That's as much as the question tells us. So how many nitrogens have we got on the left hand side? We've got 1, so we have to have 1 NO. However, we've got 3 oxygens on the left hand side and 1 on the right, so that must mean that we've got 2 waters. Now from 2 waters we can see that we've got 4 hydrogens. So now to make the charges balance we need 3 electrons. So the question told us what to write for the half equation for iron. So now what we've got to do is make the electrons work. Like so. So now we can put in the equation for reaction 1. Like that. So let's check reaction 2. Reaction 2 says it's a ligand substitution of that complex, FeH2O, iron hexa aqua, 2+. So 1 NO ligand replaces 1 water ligand. And a deep brown complex ion forms as the brown ring. So if it's a complex ion, that means it's soluble and it's charged. So let's try this out. So there you go. If you found it difficult to do this in the paper, here's how you could have read it. In which 1 NO ligand exchanges with 1 water ligand. 1 NO ligand exchanges with a water ligand. So there's 5 waters instead of 6 that you started with. Okay, so let's go to the next question then. So these are redox systems. It asks you to list them in order by adding the labels C, D and E to the table below. So you need to be looking at most negative versus least negative. So you can see that I've identified the most negative half cell because it's going to be the negative pole. So therefore, what we can do is we can see that one of them is going to be E. And we can see that the other one is C. Over on the right hand side, we can see that also this one is C. And that this one over here is D. So going down to our table, we can say that the most negative between C and E is like that, and C is the more negative out of C and D, so that must mean D is down there. So then it says that the standard cell is set up, and it's a standard hydrogen half cell. So what you should be thinking at this point is that the standard hydrogen half cell is that. And also the concentration of H plus is going to be 1 mole per decimeter cubed. So if they want you to work out the pH, you simply go to the fact that it's an H plus concentration of 1 and plug that into the pH calculation. So the next one asks you to explain in terms of electropotentials and equilibrium why the pH of the solution the hydrogen half cell decreases as this cell delivers current. So the thing to do is to write up the equilibrium so you understand what's going on and then you can say something about it, like that. So if the pH is decreasing, you're getting more H plus ions, so that must mean it's shifting to the right. So because the electrode potential of the cell, the half cell, the standard hydrogen electrode, is 0, and the electrode potential of system D is plus 0.34, so you compare the two electrode potentials and say which one is more positive. So therefore the standard hydrogen half cell equation has to be an oxidation as opposed to a reduction. So the overall equation is like that. We'll pull it down a bit. And it asks us here to label the conjugate acid-base pairs. I'm putting in a little highlight of the fact it's a very toxic weak acid, which gives you an idea of what you might want to put a bit later down the page. So that's base 2, acid 1, and that's HCN, OH minus, acid 2, base 1. So what's happening is that Cn minus picks up a proton, so that must mean that the acid, the HCN, is what could lose a proton. It could be a proton donor. So the water, that loses a proton to become OH minuses. And that gains H plus. So then it asks us to explain, in terms of equilibrium, why acidic conditions should not be used with cells containing Cn minus. So the toxic HCN is produced as the cyanide ion gains a proton when the equilibrium shifts to the right. So I think we're now coming up to the last page, second to last page. There's a little bit here on direct ethanol fuel cells. So the thing to remember here is the fuel is ethanol rather than hydrogen. So it gives you the ethanol electrode half cell. So the important thing here is the fuel itself reacts with oxygen or an oxygen to produce electrical energy. So you could say a number of things to get your next mark, but it must be an advantageous aspect of using ethanol instead of hydrogen. So here's the equation coming up for the overall reaction. So then it asks us to deduce the half equation for the reaction of the oxygen electrode. So to do this I'm going to move the page up a little bit. So if we write out the information that we've got already, in other words the equation from the top of the page, that's going to be the other half equation to the one we're trying to work out. So what we've got to do is work out how we're going to produce 3 H2Os. So the reason I've drawn it out like this is to justify two things. First of all, that. Secondly, that. So if we were to cancel like that, we can combine those two equations to give ourselves this one. So what is the half equation for the reaction at the oxygen electrode? Well, what you have to do is to break it down into its simplest form. So it just means dividing it by 3, like that. So the next bit's easy. It's just AS skills. Like that. So, final question. It was a bit of a stinker, this one, so let's have a think about it. There's a redox titration example, or at least part of it was. So, let's now have a look at what we're given. 5.25 gram sample of this stuff. So you end up with a solution containing chromate ions. So it's made up to 1 decimeter cubed in a volumetric flask. In other words, 1,000 centimeters cubed. You're used to it being 250 centimeters cubed, but this time it's 1,000, so bear that in mind. 25 centimeter cubed sample, in other words, 1/40th of the original amount, is pipette into a conical flask and an excess of aqueous potassium iodide is added. In other words, more than you need. So a redox reaction takes place between I minus, CrO42 minus, and H2O. In the reaction, 1 mole of CrO42 minus forms 1.5 moles of I2. So the resulting mixture, what you get from that reaction, is titrated with 0.1 molar decimeter cubed sodium thiosulfate, and the average titer is 25.5. So what you can use there is the fact you've got a volume and you've got a concentration. And you can do this later on, which you will need to do. Let's move the page up a little bit. Notice I'm not necessarily jumping into any questions just yet. All I'm doing is working my way through all the information and just making a note of what it means to me. Let me move the page down a little bit. In step 1, Na2O and NaFeO2 react with water, forming an alkaline solution. So from AS you should be thinking instantly that it contains OH minus. So no surprises on the first one. Now the second one, we need to go back and have a little look at step 1 again. Or at least what they tell us here. Brown precipitate. Okay, so we've got an iron complex being made. Brown precipitates tend to be iron hydroxides, don't they, if you've remembered your transition metals and their colours. So that gives you that part of the equation. What about the sodium? There we go. Job done. So let's go to the final bit, where it asks us to determine the percentage by mass of chromium in the ore. And give your answer to 1 decimal place. So my big hint here would be to always start with the moles in the titration. So that's why we do them. So let's do this systematically. So that's our starting point. We're using N equals V times C. So up at the top I've put for reference the 2 mole calculations that we may be using during the course of this calculation. So now what we do is we go to the equation, and the equation says that there's a mole ratio of 2 to 1 between thiosulfate and iodine. So we can work out the number of moles of iodine. We also know that there's a 2 to 3 mole ratio of the chromate ion to the iodine. So we can write those in now. So we can work out the number of moles of chromate in 25 centimeters cubed. We want to know the number of moles of chromate in our original sample. Original sample is made up to 1,000 centimetres cubed, 25 centimetres cubed of which was used in the titration. So that gives us 3.4 times 10 to the minus 2 moles. So what we need to do now is try and work out the mass of the chromium in the ore. We do that by the MR, or the AR in this case, times the number of moles. So that allows us to then go on and work out the percentage of chromium by mass in the 5.25 gram sample. So we're almost at the very end now. So let's pause and then just bring this page up a little bit and do the last part. So this part refers to step 2. It's quite straightforward. There's a redox reaction between I minus, CrO4 and H2O. And it gives you the two parts of the redox equation. I would certainly suggest doing the half equations first. So the question tells you that, and because you've got 4 oxygens, that will give you 4 waters, which would justify that. And then finally, that to balance the equation charges either side. We know that iodide ions, when oxidized, turn into iodine. Now what we can do is we can multiply up to give us the overall equation of this. I'm cancelling the lecture in my mind as I go. You can write it out and then cancel the electrons yourself when you do this in the exam. And that, folks, is the end of the walkthrough. Hopefully you found it really useful. If you need any more clarification, obviously come and get in touch with me, or maybe go and see one of us in subject extension. But for the time being, thanks for your time, and see you soon. Bye.